First, let's define what we mean by enterprise architecture and data architecture. Enterprise architecture is the overall blueprint that governs an organization's IT and data infrastructure, ensuring that all components work together efficiently. A subset of this is data architecture, which focuses on structuring, managing, and utilizing data effectively within the enterprise. The key takeaway here is a well-designed data architecture ensures scalability, flexibility, and performance while making trade-offs in design choices. Data architecture refers to the overall structure and organization of data within an enterprise. It defines how data is collected, stored, integrated, managed, and utilized to support business processes and decision making. So the key components of data architecture include data storage systems such as databases, data warehouses, data lakes. Then the second one, data integration processes such as ETL pipelines, data transformation. The third one, data governance and security, such as access control, compliance, and privacy policies. Then scalability and performance optimization, which includes distributed computing, indexing strategies, and so on. So there are two aspects to a data architecture as operational and technical. Operational architecture encompasses the functional requirements of what needs to happen related to people, processes, and technology. For example, what business processes does the data serve? And then when it comes to technical architecture, it outlines how data is ingested, stored, transformed, and served along the data engineering lifecycle. For instance, how will you move 10 TB of data every hour from a source database to your data lake? So in short, operational architecture describes what needs to be done, and technical architecture details how it will happen. The AWS well-architected framework provides best practices for designing reliable, secure, efficient, and cost-effective cloud architectures. It is structured around 6 key pillars. The first one, operational excellence, which looks into the optimization of processes for efficiency. Then security, which looks into protecting data and workloads. Then reliability, which ensures systems recover from failures. Then performance efficiency, which uses computing resources effectively. Cost optimization, which tries to minimize unnecessary expenses. And sustainability, which reduces environmental impact. And then Google architecture provides best practices for designing scalable, efficient, and resilient cloud applications. The first principle, which is design for automation, means automate deployment, monitoring, and scaling processes to reduce manual intervention and improve system reliability. The second one, be smart with state, means to reduce reliance on stateful services by using stateless ones when possible, which helps to improve scalability and reliability. In computing, stateful and stateless refer to how an application or service manages and retains information, or the state, across interactions. So stateful means that the system remembers information from previous interactions. For example, when you log into a website, your session and preferences are stored and the system remembers them until you log out. Stateless means that each request is dependent and the system doesn't retain any memory of previous interactions. So every request is treated as a fresh start. For example, A stateless web service doesn't need to remember what you did on the previous page. And stateless services are often preferred for scalability and fault tolerance because they don't rely on the maintenance and sharing states across different parts of the system. Then the third principle, favor managed services, means to utilize cloud managed services to reduce operational overhead and focus on business logic. Fourth principle, practice defense in depth, means to implement multiple layers of security including encryption, IAM policies in AWS, and network controls to protect against threats. Finally, always be architecting warns us to continuously evaluate and evolve the architecture based on new technologies, performance insights, and business needs. So if you click on the two column headers, they should take you to the respective pages of AWS and Google, which discuss these frameworks in detail. So you should study these two frameworks and determine how they align with the principles of data engineering architecture, which is a simple exercise I'm leaving for you to do on your own after going through the recommended reading materials. In system architecture, it's crucial to understand the distinction between domains and services, as these components form the foundation for designing scalable and efficient systems. A domain refers to the real-world subject area for which you are architecting a system. It's the area of focus or expertise that the system is intended to serve. Domains often represent specific business areas or functional boundaries within an organization. For example, an e-commerce platform might have domains like sales, inventory, and user management. Then a service is a set of functionalities or a unit of work that accomplishes a specific task or goal. Services are designed to perform specific functions within a domain. These services often communicate with other services but typically focus on a single task or responsibility. Now imagine you are designing a system for an organization that includes multiple domains like marketing, accounting, sales, and so on. Each domain might have its own set of services, but some services can be shared across domains. So in the following image, you'll notice how two domains share a service while each also has its own set of services. The sales domain includes services like order processing, invoice management, and product management. And then the accounting domain also includes services like payroll management, AR management, and invoice management. Despite having separate services for their own specific needs, both domains share the invoice management service, which performs a task common to both sales and accounting operations. This shared service is designed to accomplish the specific task of handling invoices regardless of the domain. So the key takeaway here is by properly defining domains and designing specialized services, you can build systems that are both modular and scalable, allowing different parts of the system to evolve independently while still working together efficiently. Moving on, right. So centralized and decentralized software architectures are two distinct approaches to system design. In a centralized architecture, all components or services are controlled and managed from a single central point. So this setup makes data consistency easier to maintain and simplifies management as everything operates under one authority. However, it can lead to a bottleneck as the central entity may struggle to handle high traffic or requests, creating a potential single point of failure. But on the other hand, A decentralized architecture distributes control across multiple independent components or services. Each service operates autonomously, improving fault tolerance, scalability, and resilience, since a failure in one service does not affect the entire system. However, this approach can introduce complexity in terms of system management, communication, and maintaining data consistency. Centralized systems are easier to manage and monitor, but may struggle with scaling and fault tolerance, while decentralized systems provide greater scalability and resilience, but come with added complexity. So the choice between the two depends on the system's specific needs, including performance, availability, and growth requirements. Because you have been listening to me for quite a while now, I want you to take a quick break before we learn about different distributed architectures. While you take a break, please watch the video included on this slide. It will give you a nice visualization of distributed architectures. So you can find the link to this video under week 2 materials of the reading section on Canvas. Client-server architecture and peer-to-peer architecture are two fundamental models for organizing networked systems. In client-server architecture, the system is divided into two main components: the client, which requests services or resources, and the server, which provides them. The client initiates requests to the server, which processes these requests and returns the appropriate responses. This model is widely used in applications like web services, where the server hosts the data or application and the client accesses it via a network. In contrast, peer-to-peer architecture involves a decentralized structure where each node, or we call a peer, in the network can act both as a client and a server. Peers share resources directly with each other without relying on a central server. So this model is commonly seen in file sharing systems where users can both request and provide data. P2P networks are more resilient and scalable, as there's no central point of failure, but they can be more complex to manage due to the distributed nature of the system. So both architectures have their own advantages. So client server is more controlled and simpler for centralized management, while P2P offers flexibility and decentralization. Multi-tier architecture and microservice architecture are both approaches designed to improve scalability, maintainability, and flexibility in software systems, but they differ in their structure and application. Multi-tier architecture divides a system into multiple layers, typically including a presentation layer, which we sometimes call as the user interface, then business logic layer, which we sometimes call as processing and application logic, and the data layer, which represents the database and data management. So each layer is responsible for a specific function, and communication between these layers is usually managed through well-defined interfaces. This separation helps isolate concerns, improve security, and make the system easier to maintain and scale, especially in large, complex applications. Microservice architecture, on the other hand, breaks down an application into a collection of small independent services, each focused on a specific business capability. These services are loosely coupled, communicate over lightweight protocols such as HTTP and REST, and are deployed independently, which allows for faster development, scalability, and resilience. While multi-tier architecture centralizes different functions into layers, microservices offer a decentralized approach, allowing teams to work on individual services without affecting the entire application. So microservices provide greater flexibility, scalability, and fault tolerance, but can introduce complexity in managing and integrating numerous services. Service-oriented architecture SOA and event-driven architecture EDA are two distinct architectural styles used to design distributed systems with different approaches to communication and integration. In SOA, the system is composed of a collection of loosely coupled reusable services that communicate with each other or network using well-defined protocols and message formats, typically XML or JSON. So each service is designed to handle a specific business function and can be independently deployed, updated, and maintained. SOA is focused on enabling interoperability and standardization across different applications and systems, making it ideal for large enterprise environments. On the other hand, event-driven architecture is centered around the production, detection, and reaction to events or messages. You can actually see these on the figure which I have included in my slide. So in EDA, components or services communicate by emitting events, such as a user action or system change, and other components react to those events by performing specific tasks. This asynchronous communication model allows for more scalable real-time systems as components can operate independently and respond to events as they occur. While SOA emphasizes structured service-based communication, EDA focuses on enabling systems to react dynamically to events, making it particularly well suited for real-time, highly responsive applications. Distributed architectures offer several advantages, including increased scalability, fault tolerance, and flexibility. By distributing components across multiple nodes or servers, systems can handle large workloads, scale easily by adding more nodes, and maintain operation even if one part fails, ensuring high availability. Additionally, distributed systems can support geographic distribution, improving performance and access for users in different locations. However, distributed architectures also come with challenges such as increased complexity in management, security, and data consistency. So coordinating and synchronizing data across multiple nodes can be difficult, leading to potential issues with consistency and latency. Moreover, distributed systems require robust communication mechanisms to ensure reliability and efficiency, and the added complexity can make troubleshooting and debugging more difficult. While they offer great benefits for large-scale, high-availability systems, the complexity of their design and operation should be carefully considered. So here we are going to talk about different data architectures. A data warehouse is a centralized repository that stores large amounts of structured data from various sources, optimized for reporting and analysis. It supports business intelligence activities, allowing users to run complex queries and generate insights. Then a data mart is a subset of a data warehouse, typically focused on a specific business function or department, such as sales or finance, and contains more targeted, curated data to meet the needs of that particular group. A data lake, in contrast, is a storage system that can handle large volumes of raw, unstructured, semi-structured, and structured data, often at a much larger scale than a data warehouse. It provides flexibility for storing diverse data types, but requires more processing to extract meaningful insights. Finally, a data mesh is a decentralized approach to data architecture where data ownership is distributed across various business domains, with each domain responsible for managing its own data as a product. Unlike traditional centralized models, a data mesh promotes a more flexible, scalable, and collaborative approach to managing data, particularly for large complex organizations. While data warehouses and marts focus on structured data for reporting, data lakes and data meshes emphasize scalability and flexibility, with data lakes handling diverse data types and data meshes decentralizing data management to improve agility. So this is a visualization of the four architectures I explained before. So carefully observe each one's input types, intermediary processing if there's any, and the set of downstream tasks the outputs would support. So we have reached the end of the second module. Please make sure you go through these recommended readings before attempting the weekly quiz. And if you have any questions, please feel free to drop them in the discussion forum. Thank you for listening. I will see you next week with module 3, where we will